Suppose we have a random variable x from some sample space omega to a set of n values. How can we determine its probability distribution? For that, we may use a technique called the principle of maximum entropy. The entropy is a quantity defined by this equation, and it measures the randomness of the distribution. Although we do not know anything about this distribution, we do know that it must be normalized. So we maximize this entropy with this constraint, and in this video I will explain how to solve this constraint maximization problem and finally derive the uniform distribution as a result of the principle of maximum entropy. Okay, let's start. For constrained maximization problems, we can use the method of Lagrange multipliers. So here's our Lagrangian. This is entropy, which is the function to be maximized. And here's the constraint. And this alpha is Lagrange undetermined multiplier. So we plug in the definition of entropy. We have this. Now, let's differentiate this function L with respect to these variables. And we get this. At the maximum point, this should be equal to 0. So solving this equation for pi, we obtain this expression. Now look, this term does not contain the index I. So that means for all I, this is constant. So from the normalization condition, if we sum pi's over all i's, then we have n times this factor equal to 1. Therefore, this constant should be 1 over n. Therefore, we have this uniform distribution. So far so good, but if you carefully examine the argument so far, you may notice that this condition is not sufficient for finding a maximum because the first derivative may be 0 also at a minimum point. So we need to examine whether our result really gives a maximum point rather than a minimum point. To check whether we really got a maximum point, we need to examine the second derivative of the Lagrangian. So here's the first derivative, and if we differentiate this first derivative with respect to another variable, pj, then we have this. So this delta ij is Kronecker's delta. So when I is equal to j, it is 1. When I is not equal to j, it is 0. So that means this Hessian matrix of the Lagrangian is a diagonal matrix with the diagonal elements being negative 1 over pi. So all of the diagonal elements are negative and all the off-diagonal elements are 0. So that means the Hessian matrix is negative definite. That means the Lagrangian function is a concave function. A concave function looks like this. So when the first derivative is 0, then it takes a maximum value. Therefore, the result we have got indeed gives the maximum point of the entropy with the constraint that the probability distribution is normalized. So let's recap what we have done. We have this random variable x that can take n values, and we knew nothing about its distribution except that it is normalized. And we introduced a quantity called entropy, which measures the randomness of a distribution. So maximizing an entropy means finding the most random distribution. So we maximized this entropy with this constraint by using the method of Lagrange multiplier and found out that the distribution must be the uniform distribution, which makes sense because this is the most random distribution you can get because there's no information whatsoever about each outcome. They are all uniform and there's no bias. So it's the most random distribution you can get among all possible distributions. Since we had no information whatsoever about the distribution of this random variable beforehand, this is a very reasonable result. On the other hand, if we knew something more about this distribution, for example, the mean value of the random variable or the variance of the random variable, then we may have a different distribution. A nice thing about the principle of maximum entropy is that whether we know additional information or not about some distribution, we may still apply the same principle to find some plausible distributions. Okay, that's all for this video. If you like this video, please hit the like button and subscribe to this channel. See you later. Bye.